闲话不多说了啊，让我们立刻进入今天的第二个专场——绿色化工。首先，让我们掌声有请中科院大连化学物理研究所研究员丁云杰先生，他将为我们介绍绿色化工技术中的贵金属和类贵金属催化剂的现状与发展展望。有请丁教授。
我今天就是非常高兴啊，受这个大会这个邀请，来做一下我们在绿色化工中的贵金属和类贵金属。
Catalysts to talk about their status quo and development trends in green chemical technologies. As we all know, that China has this natural endowment structure where we have a lot of coal, we don't have enough oil, and we have insufficient supply of gas. We rely upon external crude about 73.6%, and natural gas external dependence is 44.3%. Developing modern coal chemical industry is thus of key importance to the securing energy security and the stability of the petrochemical supply chain. President Xi Jinping has emphasized that we need to make sure that we go high-end in order to achieve low carbon and green development for the coal industry. In the northwestern part of China, we see in the petrochemical process there are lots of byproducts. In order to go high-end, we need to turn these byproducts into more value-added things. As you know, that about 80% of precious metal are used in the three-way catalysts that are installed in vehicles. And another aspect about the development of electrical vehicles will it have an impact on the market of catalyst. I don't know how much the impact will be or whether there will be impact, because electric vehicle uses precious rare metals such as lithium and cobalt, but it doesn't use precious metal. And the chemical industry also has demand for precious metal, in addition to chemical industry, pharmaceutical, and pesticides, as well as fertilizer industry also has demand for precious metal, though not a huge amount. There is another challenge. Precious metal-like metals have properties like precious metals. Can they replace precious metals? These are all questions that command our attention. Another aspect I want to bring out here is that transition metals, the carbides, nitrides of these transition metals. Let's take a look at their basic structure as is shown on the slide. The basic structure of the phosphides of transition metal. I am not able to, I don't have enough time to elaborate on all of them. I just want to focus on the role of precious metal-like metals, cobalt carbide, and its role in the syngas conversion. As you know that in the process of hydrocarbon production from hydrogen, for over 2,000 years, people generally believe that carbon is toxic. However, after a series of research, we found that carbides and cobalt carbide is able to achieve absorption of carbon monoxide as well as activation of CO, but it doesn't help with the dissociation of CO. Despite that, when it's inserted to the activation center of cobalt, it's possible to generate a new type of high value-added product, which is high carbon alcohol. And as you know that cobalt carbide's basic structure looks like this. For example, the 110 surface looks like this, with its properties that happen to be the basic requirement to achieve in order to produce high carbon alcohol. If you take a look at the standalone CO to CEFT activation, we have done a lot of research regarding the formation, conversion, and activity of cobalt carbide. We found out that they represent the formation center of hydrocarbons. So as you know that they're the formation center of hydrocarbons, and when people thought that carbides were toxic, they were not wrong, as they are the formation center of hydrocarbons. However, when CO and CO2C have close contact, they have the synergy, creating a synthesis center. And after a series of characterization, we have two different types of products, two different types of catalysts. As you can see on the slide, in the first type, most of it's cobalt carbide. Thanks to hydrogen, a lot of spots are generated, cobalt spots. If it's alkanes.
So on the next graph, you can see that there comes the carbon monoxide little spots on the surface. We done a lot of research and we found the mechanism is like this. So after we have identified this catalyst, we did a pilot test and we also made a synthesizer of over 100,000 metric tons. And afterwards, we made a project with 30% of the capacity to this equipment. And so now this technology is already pretty mature. It is approved by Chinese Petroleum Association, and the industry has reached the consensus that this technology is at the forefront of the world. Another team, they have done a lot of exploration, and the indicator is never higher than 6, but we can achieve 18 to 20. And you can see the certificate and accreditation as well as our press release. So the carbon dioxide emission is less than 1. It's at 0.1, and it's a CH4. Content is also very low. The alcohol very low, as you can see on this chart. So in the precious metal, what we do is we use this carbonization or carbonylation and reaction. It used to use the homogeneous reaction, mostly with iridium and the rhodium. And today I'm going to focus on rhodium as the catalyst. Well, in the past, we did start with rhodium, using rhodium as a catalyst in the carbonylation. So on the surface of the rhodium atom, there is some value 3 particles, but the activity is not very high because a lot of rhodium particles is not put in use. And then we start to look at the question that why the other teams didn't really succeed in the heterolization of the reaction. Well, we found the problem. So the activity center, so the common value bound is put together. So it's just like a person holding a kite up on the sky, and then because of the kite flies high, so the bound would sometimes broke. So what we do is we want to make the kite rope very thick and very strong. So in reality, what we do is we inserted phosphorus into the high polymer skeleton. With many different coordination bond, we keep the iridium or rhodium in place so that the iron or the particles were not separate from the core structure. So what we do is very simple. We would make the monomer like this with a 3V phosphorus H3. So this is a polymer. It's a solid. It's in solid phase. So with with the higher entropy, then the surface will be larger, and because of this reaction, there's over 17 to 80 atoms being exposed, and also the chemical stability is very high. When the rhodium particles gets sucked up to this structure, it is in the single monomer structure. From this microscope, you can see it is at 1.3 to 3 atom. That is the diameter of this of the particle, and you cannot see any of the rhodium bond because every rhodium is exposed as a atom, separate atom. We have also done many analysis to this structure, and I can say that all these and research and development has entered the industrial use stage, and all these are premium product, and we're also able to achieve the flexible structure of the hydrocarbon. So actually in the olefin market, over 90% is in the low end, and the production takes 90% of the market, but the profitability is only 10%. Now we are able to upgrade this basic oil using the hydroformylation. In the past, it was the cobalt-based system. The cobalt-based system is not able to solve the problem in this industry. So with our technology, we can solve the current problem, and it can be used in the premium applications such as specialty diesel, the high carbon alcohol, and alpha olefin, and PAO, as well as POE. So this is a totally new pathway, different from the Western approaches. So this is the oxidation diagram we have made in our lab. So this is our theoretical model. So with this research results, we used it in a industrial project, which is in operation already. It has been running for 8 months, and it overcome a problem of the coordination problem and the precious metal waste problem, and it can be used in the hydroformylation reaction that's widely used in the chemical industry. So then let's talk about the catalyst itself. So as we will know that the catalyst, in its atomic structure, the size of the atom, the phase and the crystal phases, and has to do with the activity, the selectivity, and the stability of the product. So we have developed over 10 categories of catalysts. First of all, the phosphorus and benzene-based catalyst would be harmful to people, especially to children. So what we do is we want to take the benzene out of the structure. We know that by using precious metal, we can totally remove it. But if the conversion rate has to be as high as over 99.99, it would be very difficult. But with our technology, we are able to achieve the purity at a conversion rate at over 99.99%. This technology used to be dominated by the US technology, but we developed this CHDM technology. Now 3 factories is under construction using this technology, and one of the factory is already under operation. This page you can see what are the problems and how we can overcome them. So actually in 2014, with our technology, we can already achieve the production of over 20,000 metric tons. It uses 4 kilograms of precious metal. Another 2 set of equipments and facilities are already under construction. We also use the precious metal as an assistance agent to the reaction. So within 2 years and a half, we started from scratch, from the concept design all the way to the industrialization. Now the technology is already ready to be applied to the Ningbo factory. So when we started this project, the Ningbo factory hasn't built, but now the Ningbo factory hasn't started their production, but we have already finished the research work. Well, this is another set of facilities, 8 in China and overseas. From this page, you can see the scale of our system, the cost of the system. The catalyst, although it is of low value, but it has a high, very long life. These are other works we are doing regarding the precious metal, and I think this is all of my presentation. Thank you.